Okay, so for the second part of this problem, we are going to be working with surface area of a sphere. So very similar problem, except you have to know the formula for surface area, and that is 4 pi r squared. You could look that one up. All right, so good news is it has just two variables, like all our problems so far. We're going to get into one that doesn't soon, but derivative, we're going to do SA prime. We're going to do 8 pi r prime due to the penalty. and then when I go for particular info, we are looking for SA prime, we're looking for r prime, we're looking for regular r. So I look through the problem and I say, okay, how fast is surface area increasing at that moment? Oops, why did I have two r primes? Okay. At that moment, I already know my r was 5 feet from before. I know my r prime now. I get to use my answer from there because I know at that moment r prime is 1.27 feet per minute. So I had to use both the info from part A in part B. And then number 5 is plug in. And then in that one, we're going to put in, right, we don't know SA prime. We do know an 8 pi 5 feet and r prime is 1.27 feet per minute. If I multiply those units, I'll get feet squared per minute. If I multiply 8 times pi times 5 times 1.27, you get 159.59. So you would say the surface area was increasing at a rate of 159.59 square feet per minute. Math checks out. All right, let's go to the back and do these last two problems. All right. So on this one, we have a shrink ray gun and a giant die, the kind you roll. Okay, so you have a shrink ray gun and a giant die, like the thing you roll with dots on it. You blast the giant die with a shrink ray gun. So, right, we start off with, a giant die. We're imagining this thing's huge, right? You got your 5 sides, you got your 3 and 1. Okay, and we have a shrink ray gun. Clearly, we'll make it look kind of like this. All right. Anyway, here's our shrink ray gun. Okay. All right. So we're blasting. Okay, and then it turns into a little guy. Well, it constantly shrinks. Okay. So basically, the sides begin to shrink at a constant rate of -2 feet per second. That sounds like a side prime, right? What volume are the sides changing when the sides are 5 feet? That sounds like regular S. And they ask about volume of a cube. So step 2 is volume of cube. Well, that doesn't even take looking up because it got its name from cubing, right? So we have side cubed. That's just two variables. Number 4 must be the problem that has more than two variables, huh? Now we're going to take the derivative. So derivative of this is with respect to t. We have v prime. We have 3s squared s prime. Then we look for a particular, which is particular info is going to be, we need v prime, we need s, and we need s prime. Okay, so we already found s prime was -2 feet per second, and s is just 5 feet. So v prime must be what we're looking for. Step 5 is plug in. So you start to get the groove on these. They're all kind of the same. You plug in, I don't know what v prime is. I do know that s is 5 feet, and I'm squaring it, so that'll make my units turn into feet squared here. So then when I multiply by s prime, it'll turn into cubic feet per second, which is awesome because that's what it should be for volume. So I multiply this times 25 times -2, and you get negative 150 cubic feet per second, which to me tells me the volume was shrinking at negative 150 feet cubed per second. I guess I didn't need to say negative on here because shrinking implies the negative. So you could just say the volume was shrinking at 150 cubic feet per second. All right, final problem. That was a pretty easy one. This one's pretty hard in comparison. So you went to Cold Stone Creamery and you ordered a delicious ice cream cone. The sugar cone was 5 inches tall and 4 inches across the diameter. Unfortunately, you were not able to eat it right away because you noticed 2 elderly folks in an argument over who had the best dentures. Shortly thereafter, you noticed your ice cream had melted and now was liquid inside the cone. In a furious rage, you bite the bottom tip of the cone off and let the liquid ice cream drizzle all over the elderly people. If the height of the liquid is decreasing at a rate of negative 0.15 inches per second, how fast is the liquid pouring onto the senior citizens at the instant the ice cream is 3 inches high in the cone? Holy cow. Okay, so we got our cone here. It's 4 inches compared to 5 inches high, right? We got the broken bottom, we're dripping, right? We got our elderly couple here. Got his glasses. He's mad. He's got his arms in a defensive posture, right? Sitting on a bench. All right, so kind of got this situation going on. Here's the other person. They're an elderly couple, so we'll put her glasses on. She's looking this way and got her arms crossed. Ooh, she's mad. She's probably not even talking to him. Okay. I don't know what he did, but he messed up somehow. Okay, so anyway. Whoa. So really, what you need to notice about this is at any point, the ice cream is going to be at a certain height and a certain radius. So it might be more beneficial to me to know that this is 2 inches instead of 4 across. I want to know 2 inches radius. So the ice cream is like this level. You know, it's going to be dripping down. So the H changes and the R changes the whole time. So on number 3 here, well, I don't even know. Number 1 was read it. Number 2 is this. Number 3 is volume of a cone. I think we had this in a couple problems. V equals 1/3 pi r squared h. And when you look at this, frowny face because too many letters. So there must be something in this problem where I can unlock one of the letters. And it's right here. This 2/5, the cone's radius to the cone's height must be the same relationship as the ice cream's radius to the ice cream's height. So r over h is going to equal 2 inches over 5 inches. The inches go away. Do a little cross multiplying, and then you get to this stage where you got to decide, do I want to get rid of the r's or the h's? And when I look back in the problem, since they talk about what the height is, and they talk about what the rate the height is going down, I want to get rid of r's. So if I would have had a different problem, you know, if they would have been talking about the radius, I would have had to get rid of the h's. So here, you're going to sub that in for r. So you're going to say v equals 1/3 times pi times radius, which is 2/5 h times, and that's squared, times h. So now it's just some math here, right? When I square that, I get 4 over 25h squared. And in the end, I'll have an h cubed, I'll have a pi, then top times top, bottom times bottom, you get 4 over 75. Now I have it down to two variables, so I can finally take the derivative. So v prime, and then I got 4 over 75 times 3, which is 4 over 25. We have pi times h squared h prime. Implicit differentiation. Then I look for my particular. See, I'm labeling this, so it's a good idea when you take this thing to label your stuff. So we're going to have particular information of, let me see. So we got this height is decreasing, so that's an h prime of negative 0.15 inches per second. We have h at that particular time is 3 inches high. V prime I don't know, but now I can go ahead and plug stuff in. So V prime equals 4 over 25 times pi times height squared. That would be 3 inches squared times h prime, which is negative 0.15 inches per second. So I multiply that out, I'm going to get inches cubed per second, which is cool, because that sounds like a volume change, right? And if I do 4 over 25 times pi times 3 squared, which is 9, times negative 0.15, you get negative 0.68. So you'd say the ice cream was pouring out of the cone at 0.68 inches cubed per second on the old folks. That's not cool. That's not an appropriate reaction to losing some ice cream. Anyway, that's the rest of the problem. So you got a little stuff on implicit. You got to know how to do it with the related rates problems, which are kind of crazy. All right. Hope that makes sense to you. And yeah, do some good studying.